And then move on to the last talk for today is Jarrett Johnson, Extreme Primordial Star Formation Enabled by High-redshift Quasars. Jarrett, go ahead.
Great. Yeah, I appreciate the chance to speak with you all today. And the question I'm going to be addressing in this talk is really, is it possible, although perhaps not necessarily likely, but is it possible that with future observational facilities we'll be able to detect primordial star-forming galaxies? And I'd like to kind of couch that topic in a bit of the historical context. So I've decided to make a timeline going back now 20 years of the sort of number of claims that we've seen for possible Pop3 detection and searches for Pop3 star-forming galaxies. This goes back to Malhotra and Rowe's paper in 2002, where they claimed potential Pop3 powering of a Lyman alpha emitting galaxy at redshift 4.5, and it extends now into 2020, actually, with a couple of recent papers, one by Van Zelle et al., claiming potential Pop3 source in a strongly magnified field at redshift of 6.6. So there's a lot of activity that's been undertaken, but of course there's nothing definitive in terms of a firm Pop3 detection. So those types of first stars remain elusive. This kind of thing could change, though. The state of the field could change. Of course, we have new facilities coming online, which have as their goals to peer deeper into the early universe and search for such objects. Principal among those is probably the James Webb Space Telescope, which is still scheduled for launch in 2021. It will replace the Hubble, and of course is optimized in the infrared to do these types of searches. It's not the only thing, however, that we've already heard today mention of the extremely large telescopes, the sort of 40-meter class telescopes that will come online a few years later. Will also push our boundaries back into the early universe. So right now, it's actually critical, I think, to make predictions for where primordial objects could be detected or how they could be detected, because these observatories are going to be coming online, and those predictions will be needed in order to strategize how to use those facilities. So when you ask the question of how can you find primordial galaxies, it's sort of unpacking that. One of the questions that comes up immediately is, well, which population 3 stars are you really hoping to find, right? So the first stars we believe formed in high redshift mini halos, maybe at around a characteristic redshift of 20 or so, and dark matter halos with masses of order 10 to the 6 solar masses, maybe. And there's a nice, I've taken a nice figure from Hirano's paper showing sort of the mass scale of stars that you expect to form in those objects. And it's been known since the planning stages of James Webb, right, that those objects would certainly be too dim for James Webb to detect in the absence of some kind of extreme gravitational magnification, maybe. And it was thought that you may have to have a collection of population 3 stars in a cluster, maybe as massive, upwards of even 1 million solar masses or so, for a definitive detection. And so this points you immediately at sort of a couple of the characteristics that you'd expect for a Pop3 cluster to have in order for it to be detectable, right? One of those things is a large stellar mass. You want it to be bright, of course. The other is actually a low formation redshift. If you can detect something, or excuse me, if a cluster forms at lower redshift, redshift 6, let's say, as opposed to redshift 20, of course you have a better chance of detecting it as well. So I'm going to go through both of those sort of criteria one by one. The first one is really what's required for Pop3 stars to form at relatively low redshift. And there's actually a bit of observational evidence, at least on the front of the basic ingredient for primordial star formation, right? Which is that you have primordial gas available. So now we have observational evidence from Lyman Limit and damp Lyman alpha systems that have been observed all the way down to redshift 3 or so that are consistent actually with those gas clouds being uncontaminated, being primordial in origin. So from the empirical side, at least, there is at least evidence for the basic ingredient for primordial star formation way down to low redshift. On the observational side, you also have evidence that population 3 star formation extended down to low redshift. This comes from a body of increasingly sophisticated cosmological simulations that have been done over the last 10 years or so, showing that star formation, the Pop3 star formation, though it starts at redshift 20, does continue steadily down, maybe to redshift 6 or even lower redshifts. This is a plot from one of our papers, and you can see the population 3 star formation rate is shown by the dashed lines there. The key point here being that it does continue down until the end of the simulation of redshift 6. So you do expect from the theory side as well to have some primordial star formation taking place at low redshift. So then the next question, right, is if you do form population 3 stars at low redshift, how many can you gather together in a cluster, and can it be bright enough to be detected? The main way that we envision primordial gas collapsing to form large clusters is really by delaying its collapse until you have a large gene's mass of potentially a large influx of gas ready to form stars. And this is usually envisioned as happening in an ionized region of the universe because the gas is maintained at an elevated temperature and is only able to collapse once a lot of gas is assembled. In a typical ionized region of the universe where the gas is maybe 10,000 Kelvin or so, it's really only in halos with masses of about 1 billion solar masses or so that you may expect the gas to finally collapse. Now, keep in mind, this is 1,000 times larger already than the many halos at redshift of 20, where you may expect the first stars. And so you have at least potentially a large reservoir of gas from which to form a relatively bright cluster of population 3 stars. Now, the key point here is that if you not only look at a sort of run-of-the-mill reionized region of the universe where the gas is 10,000 Kelvin, but instead look at a special region of the universe where it's heated to much higher temperatures, there's the potential for even more massive halos to host the first episodes of star formation. In particular, I'm thinking of the regions around high-redshift quasars. So we know that high-redshift quasars are there, and we know that they emit copious X-rays, which heat the gas to very high temperatures, maybe approaching even 1 million Kelvin in the IGM. At these types of high temperatures, it's really a mass scale for the halos hosting those first stars that approaches something of order 10 to the 10 solar masses or so. So this is really the extreme case, the most massive halo you could envision hosting the initial phases of star formation. But keep in mind, right, the key point here is that the reservoir of gas in a halo that large is so large itself that even at a very small star formation efficiency, so even if only a small fraction of that gas forms stars, it may be a relatively bright Pop3 cluster that can form, and maybe something of order of 1 million solar masses that would be definitively detectable by James Webb. So one of the observational results that got me interested in looking at this scenario a bit more closely is from Goto et al. In 2017. I've taken a plot from that paper here. What they did was a search around a high-redshift quasar at redshift 6.4 to look for Lyman alpha emitters, and actually found only an upper limit. They found far fewer than they would have anticipated if those things followed the luminosity function at redshift of 6. This seemed to imply that the feedback from the quasar was actually suppressing star formation in relatively low mass halos. And in fact, it was consistent with suppression of star formation in halos of about 10 to the 10 solar masses, just the mass scale that I mentioned in the last slide that you'd expect potentially around a high redshift quasar for star formation to initially begin. And so this is, some observational evidence that we already have that's consistent with the picture in which you may have the stage set for a burst of relatively bright primordial stars just in the surroundings of high redshift quasars. So motivated by some of that work and what I've shown already, Aishin Aikutal, postdoc here at Los Alamos, and I decided to look at the evolution of that primordial gas as it collapses into a halo of that mass scale. And we took a simplified approach. I won't go into the details of the calculation shown here. I'll just draw your attention to the sketch at the top. The basic picture we have in mind, right, is that there's a supermassive black hole accreting gas in a high redshift quasar, and there's an accompanying stellar population in the host galaxy. All of these objects are producing X-rays, Lyman-Werner radiation, optical and infrared radiation that has an impact on the chemistry of the collapsing primordial halo. And then we ask the simple question, what happens to that gas as it collapses, given that it's subjected to such an intense radiation field? So what we found actually is that there are two basic possible outcomes that we'd anticipate. The first is that if the gas is able to cool, you may anticipate a population 3 stellar cluster forming, maybe one that's very bright because of the sheer volume of gas in the reservoir. The other one is that if the gas is maintained at an elevated temperature, you may have the scenario taking place, which we've already heard about today, the direct collapse black hole outcome. And there's sort of a characteristic distance from a high redshift quasar within which you might expect a direct collapse black hole to form because the gas is maintained at high temperature. And what we found here for sort of typical high redshift quasar black hole masses and stellar population mass, something of order 200 kiloparsec or so from a high redshift quasar that you could have direct collapse black holes forming. So keeping that length scale in mind, a couple of 100 kiloparsec, we can now ask another question, which is really a key one, and that is, what about metal enrichment? So metal enrichment we would expect to occur from high-redshift quasars. Of course, they pump out the radiation that sets the stage potentially for a burst of Pop3 star formation, but the metals could enrich the gas and actually prevent Pop3 star formation as well, at least in principle. What's been seen in observations, however, though, is that metal enrichment and the outflows from high-redshift quasars appear to extend only out to maybe kiloparsec or maybe a couple or a few tens of kiloparsecs from the host halo. And that is a shorter length scale than the sort of hundreds of kiloparsec we're looking at in terms of the distances of these interesting primordial objects. So I don't think that necessarily metal enrichment is going to be a game or a showstopper in preventing this scenario from taking place. You also incidentally see the similar results from what's found in observations in recent cosmological simulations. So another thing that we went on to do is actually look at, how bright would you expect these objects to be if you form a cluster of population 3 stars, again, assuming a pretty low efficiency for star formation, but a very high halo mass. You can see in the plot here, we have Lyman alpha flux as a function of redshift for host halo masses corresponding to 3 different virial temperatures between 10 to the 4 and 10 to the 6 Kelvin, 10 to the 6 being really that extreme upper limit you might expect for initial stages of star formation in the vicinity of a quasar. And the key point here is that we've also plotted the NIRCam flux limit expected for James Webb for an observation time of about 2 times 10 to the 5 seconds, so a couple of days maybe. And the point here is that you really do need to have these stars forming in really massive halos in order for James Webb to detect them. So you really do have the best chance potentially of finding Pop3 clusters in the vicinity of quasars where the most massive clusters could form. Another point related to that, though, is actually that direct collapse black holes, if they form instead of just a simple stellar cluster, because those are powered by accretion onto the black hole, they can be brighter, and they may also be more long-lived sources, so that surveys looking for these things may actually be expected to find more direct collapse black holes than Pop3 stellar clusters, for those reasons at least. So I'll come to essentially my last slide here, which is to make a point, which is key, and that is that there's an elegantly simple observational strategy for testing this scenario and potentially finding primordial stellar populations in the high-redshift universe. And it doesn't involve doing a deep, wide, very time-consuming survey. The nice thing about this scenario, right, is that you already know where to look for these objects. We already know where high-redshift bright quasars are, and you can do individual pointings of those objects and look around their vicinities and see if you find any of these interesting primordial objects, be they Pop3 clusters or direct collapse black holes. I illustrate that point here by showing the James Webb NIRCam field of view sort of superimposed on the Wu quasar from the discovery paper in 2015. You can see how large that field of view is, and I've also shown a circle here of that length scale within which you may expect Pop3 clusters or direct collapse black holes to form. You can see that the James Webb field of view fits snugly over that. So with just a few pointings, you might have a chance at finding something really interesting in a limited amount of observing time. And with that, this is my concluding slide. I'll leave it up in the interest of time and take questions. Thanks.
Thanks so much. It's exciting. I will allow people to applause while we're waiting for questions. Any question for Jarrett? Sorry, any question for Jarrett? So Jarrett, can you show the prediction of how bright these Pop3 clusters are again?
Yeah, let me share once more. Yeah, so maybe this is what you
okay.
would like to see. Yeah.
I'm just wondering. So the JWST NIRCam limit, that limit, in which sense that's the limit? And how long exposure?
Oh, I'm sorry. Yeah, this is something I sort of glossed over in the bottom left. It's this is for a 200,000 second exposure, so it's a lengthy exposure.
Okay, thank you. We have one more question. Would the duty cycle quasar affect the formation of these Pop3 galaxies?
Yeah, absolutely. In principle, it does, right? Because if there's, I mean, the star formation has to be suppressed from the time those are mini halos all the way up until they're these relatively massive halos north of 1 billion solar masses. The star formation has to be suppressed that entire time. So the quasar probably has to light up early and suppress star formation, for hundreds of millions of years. Of course, if it flickers on and off, that could leave windows when primordial star formation could take place, and you miss out on this scenario. So that is a really good point. One of the things we looked at in the paper, though, is I'm flipping through here. You can sort of mock up the kind of radiation field as it would evolve in time, starting from the seed black hole at earlier times. And if it's steady accretion, it looks like you have a chance of actually accomplishing that suppression. But I completely appreciate the question that if there is a duty cycle, it complicates the picture for sure.
Thank you. We have one last question before I think we close off for today. So Rohan has the last word. How would you confirm sources around these quasars as Pop3 clusters? Will their signatures differ from the canonical expectations in any way due to the quasar environment?
Yeah, that's a wonderful question, right? It's a broader and really key question that I haven't even attempted to address in this talk. How do you prove anything's a Pop3 source, right? I think what you'd have to do here, of course, going back to what Eduardo said to open, there's the distinction between detection and identification, right? James Webb NIRCam can probably provide a detection, but the identification will be the job of probably the NIRSpec instrument. You'll have to take a long spectral measurement to see if you find lines like the helium-2 1640 line, which is thought to be a signature, and push down upper limits for the lines from metals that may be there as well. But how far you can afford to do that and really prove something as Pop3 is a fantastic question. And I don't have a great answer for that.
Thank you. As for the next JWST proposal cycle, I guess.
That's right. I think.
Yeah.